So we could go all the way from a carboxylic acid, sort of back to a carboxylic acid. That's going to be our end step. But let's just go through each one of the acid derivatives, carboxylic acid derivatives. So we can start by making a acid halide with our COCl2. And then we could form an anhydride from that. And to form an anhydride, you need sort of a deprotonated carboxylic acid. So you would take this and it would have a deprotonated OH group. That would attack here, kick these out. That would give you O. We'll have a minus there. Our chlorine's still here. And I left this one blank right now because I'm going to really pay attention to how everything's connecting. So I've made a bond to the oxygen. So this is going to be an oxygen. And then the oxygen is bonded to 1, 2 carbons. So 1, 2. And the second carbon has that double bond to O. Okay. Now what I can do is take my electrons from here, put them back there, and kick off chlorine. That's good. I've now reformed this. I've got that O here. And if I just sort of flip this upside down, since I've replaced the O to be here, I'm going to get 1, 2 carbons and a bond to oxygen there. Here's an anhydride, an acid anhydride. If we want to take that acid anhydride and convert it into an ester, all we need to do is add some alcohol. So let's do CH3OH. Remember, this has electrons, so we can take this, attack one of our carbonyls there, kick off these electrons. We're going to get that O minus. We're going to get our O is still here, and we still have this here. But now we've added, I'll put it down here, an O that's bonded to an H that's bonded to CH3. This gets a positive charge. All right. We can protonate this here using something in solution, or if you want to just maybe even show this hydrogen going over here, that would work. We'll do that. It's not really how it works, but it's the easiest way to think about it because you're doing two things in one step. Okay, now we've got O minus attached to an O that has that attached to it, and now this has a positive charge and a hydrogen on it, and we still have this OCH3 group. Okay, cool. Now we can bring our electrons back down and kick out that positively charged oxygen, giving us O double bonded. We're going to take this and put it where the anhydride part was. So we're going to get an O with a CH3 group on it. And this part effectively has made OH, another carboxylic acid. Cool. This is our main product. We're just going to focus on it. What if we want to take that ester and make it into an amide? Okay, well, let's take the ester, O, and let's add in NH3, which has a lone pair. That lone pair is going to attack that carbonyl carbon. This is going to kick off, and we're going to get a negative charge. We're going to get that O still, and now we have an H3, and it has a positive charge. Okay, again, sometimes it's just easier to think about it this way. Let's make this attack here, and let's give those electrons back to that. And now we'll get O minus with an O that has a hydrogen on it now and a bond that's positively charged. This is going to be NH2 now. That's good. It's neutral. And so now we can pull our electrons back into our bond and kick off the oxygen species, the what sort of like a alcohol species, right? And what does that give us? That gives us O double bonded to carbon. And now instead of that OH, that ester group, we now have NH2. That's good. Can we take that NH2, that amide, to a carboxylic acid? We can. We just need to add some water, either H3O plus or OH minus, just depending on what your conditions are. These will obviously both be in water. And let's just use OH because it's less steps, right? So we can attack the carbonyl carbon, push the electrons onto oxygen. Our NH2 is still in solution. Here we've got OH, and now all we need to do is bring our electrons back down and kick off the nitrogen. And that is going to give us O and an OH. And so now we're back to our carboxylic acid where we started. And that is all of the acid derivatives from starting with carboxylic acid, going to a acid halide, going from an acid halide to an anhydride, going from an anhydride to an ester to an amide, and an amide all the way back to a carboxylic acid. So this is sort of like a cycle, and you can think of it like that. And remember that you can do other things with these individual species, like you could reduce the amide to an amine instead of going to a carboxylic acid. You could take the anhydride and turn it into, you could go straight from an anhydride to an amide, or you could go straight from an anhydride to a carboxylic acid, or to an alcohol or a carboxylic acid. And they all use very similar steps. So you used OH, you use an alcohol here, and here with the amide, you used an OH. So just think about what you're trying to make. If you're going from an anhydride down to an amide, then you need to add NH3. It's the same step. If you're going from an anhydride to a alcohol or to a carboxylic acid, you're going to need to use water. And that's just because instead of adding this CH3 group attached, which we end up with over here, we just want this to be OH, not O with a group on it. So you would just use water instead. You would replace this carbon group with another hydrogen. And so just sort of knowing that you can do this and get back to where you started is really helpful, because you can sort of pick up anywhere in the middle of these, start with an acid, end up with an ester. You can sort of get there from any point in the cycle of things.